to thank all the organizers, for people from the Institute for putting together this wonderful workshop. It's a great pleasure to be here. First time in Florida and University of Miami, and it's gorgeous. So from the title, maybe it's easy to tell that this talk will focus on some mathematical predictions that come from physics. And indeed, physics usually gives some interesting guiding principles for you to develop mathematical theory. And most of you already know that the theory of topological recursion has an intimate connection with quantum physics in 2 dimensions. One cool thing about physics is that the dimension of the physical system is sometimes flexible. For example, as most of you know, 2-dimensional quantum physics is closely related to 0-dimensional matrix models. So matrix models are usually given by some finite dimensional integrals, and they can be viewed as a special type of path integrals, but in 0 dimensions. And there can also be relations between 2-dimensional physics and higher dimensional physics. A well-known example is a relation between 2D conformal field theory that has already appeared in the program with 3-dimensional topological quantum field theories, which also has appeared. There are also connections between 2-dimensional physics with physics in even higher dimension, like 4, 5, or 6 dimensions. But today, we'll be focusing on 3-dimensional TQFTs. And the goal of this talk is to introduce to you some new families of 3D TQFTs. And because all of this connection, after introducing you these 3 TQFTs, I will ask you whether you can observe some kind of recursive scheme where these new families fit. And the way that we will find these new 3D TQFTs is by counting BPS states in M theory. But this sounds a little bit scary and fancy. But before being scared by this, you should first question or should first feel a little bit suspicious, because we all know how to count, and we all know that the end result of counting is usually some integer or a sequence of integers. But do we know any 3D TQFT whose partition functions are always integers? So I'm kind of new to the world of quantum topology, and I don't know any 3D TQFTs with this property besides the trivial ones. Indeed, the most familiar 3D TQFTs are Chern-Simons theories, that are given by a compact Lie group G and a level K. later I will write a particular partition function of a particular Chern-Simons theory, and you can see that it's kind of a little bit far from being an integer. There is another class of theory known as Rozanski-Witten theories. And they are labeled instead by a hyperkähler manifold and if you study this, then it will also become very soon clear that it's hard to find a hyperkähler manifold such that you always have integer partition function. So let me give you an example of Chern-Simons theory partition function. So let's consider maybe the case where the group is SU2, and then the level can be taken to be an arbitrary integer. The partition function is also known as the WRT invariant. And we will consider first the WRT invariance associated with the length space L5, 1. So this is a quotient of the 3 sphere by the action of Z5. So this will obviously be a function of k, and it turned out to be a rather messy function. So let's first pull out some factors to make the right-hand side of the equation to be as clean as possible. And then you will first start with 1 over square root of 5, which is not an integer. And then we'll have a term like q to the 1/5 minus 1. So here I have already used the notation q equals to 2 pi I over k. It turns out that, in a sense, q is a very natural variable in Chern-Simons theory. Then we'll have another term that is kind of hard to rewrite only in terms of q. E to 2 pi I k over 5 over 2 times square root of 5 plus minus 1 minus square root of 5 q to the 1/5 minus 4. And then another term that look rather similar, e to minus 2 pi I k over 5 over 2 times square root of 5 minus 1 plus square root of 5 q to the 1/5 minus 4. So if you are given WRT invariance for some 3 manifolds that looks like this, is there any systematic way to extract integer numbers out of this? So naively you say no. So WRT invariants are just fundamentally non-integral. But it turns out that if you embed WRT invariants into string theory, then string theory will tell you that actually you can get integers. But you need to first decompose WRT invariants into some basic building blocks. And using string theory, we came up with the following conjecture, or maybe philosophy. So this first appeared as conjecture 2.1 in a joint paper with Sergei Gukov, Pavel Pushov, and Kumar-Vafa. And then there are further improvements in the work of, for example, Gukov, Melnescu, and the work of Chern, Gukov, Park, and Sopenko. So the basic idea is that the WRT invariant of any three manifolds can be decomposed into some rather canonical linear combinations of these fundamental building blocks that I will denote by Z hat. When you send Q to be a root of unity. So here, Z hat, there will be finitely many of them, and they are almost Q series with integer coefficients modulo overall rational power. And the coefficients C are simple functions, simple coefficients that only depend on data like the choice of the group, the level K, and a little bit of information about the three manifolds that enter through the torsion part of the first fundamental group, equipped with linking form.
Level A runs.
So here, A is valued in certain set that I will specify in some simple examples. So the understanding of this decomposition is getting improved. So in the case that is relevant for, maybe let me first erase this. In the case that is relevant for this example that I just erased, namely G equals SU2, M3 being a rational homology sphere, then CA is given by the following simple expression. First of all, A is valued in the set, the torsion part of H1, M3, with integer coefficient, quotient by a Z2 action. And this Z2 will send A to minus A.
homologous sphere that H1 coincides with the torsion.
Hmm?
If it's because rational homologous sphere, the torsion of H1 is the whole H1, yeah?
Yeah, yeah. So this is rational homologous sphere plus well. So for the expression that I'm going to write, the conjecture is going to be true for a class that is slightly larger than the rational homologous spheres. Basically rational homologous spheres. But of course, you are completely correct that for random homologous sphere, of course, taking the torsion part is meaningless because everything is torsion. And in this case, these coefficients will be given by the simple expression. It's a summation over B, again in this set, e to I, k, linking form of B and B, and the matrix SAB, where SAB is given by e to 4 pi I, linking form of AB plus e to minus 4 pi I, linking form of, again, AB over the size of the stabilizer group at A of the Z2 action and the size of stabilizer group at B over square root of the torsion part of H1 and 3 with Z coefficient. So again, WA here denotes the stabilizer of this Z2 action at A. And the linking form, as a reminder, is a map from two copies of H1 to rational numbers mod Z. So indeed you can see that these coefficients C are simple functions of the group, and K and homology of the 3-sphere. Oh, which 2 pi I?
Well, the E of the IKF.
Oh, yeah.
Is 2 pi.
Yes, 2 pi. So what happens to the simple case of L5, 1? In this case, H1 or the torsion parts of H1 is Z5, and so A can take 3 possible values. It can be either 0 or 1. So plus and minus 1 are the same, so I will just write plus 1 and then 2. And then there are 3 different Z hat. Z hat 0, Z hat 1, and Z hat 2. And it turns out that in this case they are very simple Q series. For Z0, it does not even depend on Q. For Z1, it's Q to the 1/5. And for Z2, it turns out to be 0. In this case, it's rather special, but in general, the Z hats turn out to be infinite Q series. So then you can easily check that the conjecture is correct in this case. So for example, you can easily compute this S matrix, and this will be 1 over square root of 5, 1 half, 1, 1, 1, 1, 1 half, times minus square root of 5 minus 1, 1 half, square root of 5 minus 1, 1 half, square root of 5 minus 1, and 1 half minus square root of 5 minus 1. And then you can bring this into the conjecture and then check that these simple integers indeed can reproduce for you the WRT invariants for length space L51. And you can also check that this works for more general classes. So for example, it certainly works for all length spaces. It worked for a very large class of Plum 3 manifolds. And now with the work of Sergey and others, is tested for more general 3 manifolds, such as mapping tori. But why would you expect something like this to happen? And since WRT invariants turn out to be some particular linear combination of the Z hat, you want to also think about other possible linear combinations that give you 3D TQFTs. So for that purpose, one need to understand a little bit where does these numbers come from. It turns out that doing BPS counting in M theory is not as hard as it sounds. So the relevant geometry is the following. Recall that M theory lives in 11 dimensions. And the geometry will look like the total space of the cotangent bundle of M3 times the total space of the cotangent bundle of 2 disks times a real line. But M theory, just like real world, had some particles. One of the particles in M theory is known as M5 branes. And they are 6-dimensional. And this 6-dimensional M5 brane will wrap the zero section of the cotangent bundle of M3 and the zero section of the cotangent bundle to D2, and then times the same R direction. So if you know a little bit about Witten's statement about the relation between Chern-Simons theory and string theory, you may not be entirely surprised by this geometry, because Witten told us before that Chern-Simons theory is a topological open string or open topological string on T star of M3.
Where SU2 is this geometry?
So here, what I wrote is M5 branes. So it can be one brane or two branes. Yes, if it's SU2, then you put 2 branes. For SUN, you want to put n branes. There are also ways to engineer other type of ADE groups. So So this is geometry, but what are the BPS states? It turns out that the BPS states are given by another kind of fundamental particle in M theory known as M fibrils. These are now three-dimensional. And they live here as some holomorphic disks. So let me maybe use the letter C for a holomorphic disk times a point here and times the same line. So you see that the problem of counting BPS states in this geometry can be rephrased to a geometric question.
What is going on the boundary of the disk?
That's an important question, and that's where these A's come from. So I will address it a little bit later. So BPS states give you a space. So you have a space of BPS states, and let's denote that as maybe H BPS. And to get interesting invariants, we need to find some additional structure on this, because this can be easily infinite dimensional, and without additional structure, we're not getting interesting numbers. One thing that one first noticed is that there are isometries in this geometry. This disk can admit a U1 action, and I will denote this one by U1Q. Therefore, on this Hilbert space, there is also going to be a U1 action, and one can decompose this into graded subspaces. And then
geometrically it consists of what?
Geometrically, this Q is related to the area.
BPS consists of what?
Oh, they are just generated by these homomorphic disks. Linear span of independent homomorphic disks.
Linear span of non-linear objects, linear combination of holomorphic disks. We could just some sheets. What is it?
We'll see. Okay.
Sorry. So there are some basic homomorphic disks that cannot be decomposed, and then they generate one-dimensional subspace inside this space. And it's a linear span of all these basic homomorphic disks. But there is another way to slightly refine this space, and that's related to the question that Maxime asked. So for a homomorphic disk C, one can ask what is the boundary of C, and that has to be living on the three manifolds M3. That's a basic setting of topological open string. And if one look at the homology class of gamma, then it turns out that the BPS states that we want to count has to be in torsion part of H1. Therefore, this space is now graded by first an integer coming from the weight of the U1Q action, and torsion part of each one of the three manifold.
What happens on the boundary not of holomorphic disk but of disk D2?
Of disk.
D2, not of holomorphic.
Oh, this kind of disk?
Open or closed, boundary is included or not?
So there, I think if so, you want to look at a configuration that minimize energy. Such disk, I think, will not minimize energy. But in the same class, it's those disks that all map to a point that minimize the energy in the same class, and this will contribute to z hat 0 with 1 or -1 depending on the sign.
Strictly speaking, the boundary of a disk is always null homologous, even if the disk is not embedded, even if it's immersed.
Yeah. So here,
Even the photons and boundaries.
so here by the word disk, I mean that it's not strictly speaking always a disk. It can be so the boundary of the disk can be actually a union of circles. So here I'm using maybe I should just call this an open holomorphic curve. So it does not has to be disk. Everything has to be counted.
Genus of curve is 0.
In this case, I think only somehow genus 0 curves contribute for some reason.
Since you put question marks on
Yeah, I think it's an open question whether higher genus curves are counted here. But I suspect that only genus 0.
here with manifold.
So annulus is allowed.
Hmm?
So
Yeah, they are allowed.
But then it doesn't have to be torsion at all.
It doesn't have to be torsion at all, but from a little bit physical consideration, you realize that you want to count these massless states, and then this has to be such that this is a torsion. Further questions about geometry? Yes.
Basically, your BPS numbers will be a number of these disks with prescribed homology class and other discrete values.
Yeah,
That's what we
exactly.
found.
Exactly. And so one gets this kind of structure on this space, and then one can encode the dimensions of all these subspaces into a Q series labeled by an element inside here. I forgot to quotient by the action of Z2. And this is where this Z hat comes from. So I believe that Sergey will continue with Z hat on Thursday. So I will just add a few remarks about Z hat. First of all, this A can be viewed as boundary conditions. On the boundary of the two disks here. So they are related to some equivalence class of physical boundary conditions that one can put here. And many other boundary conditions are linear combinations of them. So for example, if you want to get WRT invariants, that would correspond to a particular boundary condition. And that turns out to be a linear combination of these more basic boundary conditions. And further, previously I have assumed that the three manifolds does not have a boundary, but you can also define Z hat if the boundary of three manifolds is not empty. And I believe that on Thursday, Sergey will particularly talk about the case that the boundary of the three manifolds is the two torus. And then in this case, he will show you that this Z hat also satisfy some kind of recursion relation. And it turns out that if you consider Z hat associated with three manifold that has boundary, you can also do some cutting and gluing. So it seems that Z hat demonstrates some TQFT-like behaviors. So in the case that the boundary is not empty, there will be an additional parameter. And then, so it will depend on Q and another variable X. And if you expand it, it's still going to be numbers. You'll be serious in Q and X. Yes?
So if this M3 is the complement of a knot,
Mm-hmm.
is this related to some knot?
It's related to, so just like the case when M3 is closed, this is related to WT invariants. In this case, they are related to the Jones polynomials and Cutler-Jones polynomials. And the recursion relation that they satisfy is very closely related to the recursion relation given by the quantum A polynomials.
Critical points in Chern-Simons, they mean anything with Simons.
So in a sense, so critical points of Chern-Simons theory are characterized by holonomies. But this is in a sense the dual to these holonomies. So this S matrix is in a sense this discrete Fourier transformation that brings you from one basis to another basis.
There's only one Z cut, right? Because according to your rules, the torsion of a knot complement is
So the rule is for the case that M3 is actually closed. In the case that it's a non-complement, then I think it's the label. There will be more labels. Sergey will talk more about this. So. I want to make a quick remark about Jan's question relating to critical points. So Z hat, in the expression that relate WT invariants to Z hat, there is an expression that looks like SAB, summation of this times an exponential. And then if you sum, so here you are supposed to sum over both A and B, but if you only sum A, not B, then what you get is closely related to a perturbative expansion of Chern-Simons theory at the critical points. So I think maybe Sergey will also talk about this in his talk. So previously I was claiming that these z-hats are fundamental building blocks of three manifold invariants. And now we see that you can start from this to get WT invariants with different level. But if they are really fundamental building blocks of three manifold invariants, you should also hope that there are some different combinations of these z-hats that produce some different TQFTs that are not Chern-Simons-like. So, is there any new family that we can obtain by doing taking some different linear combination? It turns out that this is possible because in the geometry we have a disk D2, and previously we are considering boundary conditions, and there is a boundary condition such that this disk or fields on this disk behave like wild Hitchin systems. So there are, remember that in the total space there is T star of this disk, and the brain can vibrate along the T star direction, and these are Higgs fields, and we want the boundary condition on the edge such that if you map that to CP1, the Higgs field will have higher order poles. And they will behave like the Higgs field in wild Hitchin system. Sometimes this is also referred to as irregular Hitchin system. And in the case that G is SU2, there is a particular nice family of such boundary conditions, and they gave rise to wild Hitchin systems with a spectral curve given by x squared plus z to the k, where k is integer larger than or equal to 3. And in this case, we get, again, a 3D TQFT. But these are going to be 3 TQFTs of Rozansky-Witten type. And recall that Rozansky-Witten theory depends on choice of target. In this case, the target will be the corresponding moduli space of the wild Hitchin system. And if you don't know Rosansky-Witten theory, you can think of it as the analog of a B model, but in 3 dimensions. It is sometimes referred to as the 3D B model. And indeed, this moduli space admits a hyperkähler metric, and just like the usual Kitchen system, this space is also the total space of a complex integral system. So in the simple case that k equals to 3, this moduli space looks like an elliptic surface with only one exceptional or singular fibers. So away from the singular fiber, these fibers are going to be elliptic curves. Or these special points here, you'll have a fiber that looks like the following. Such singular fibers in a family of elliptic fibration was classified by Kodaira, and this is type 2 singularity in his table. And so there is a boundary condition such that you get Rosansky-Witten theory to this target space. But if you know a little bit about Rosansky-Witten theory, you will know that it's sometimes called a TQFT, but strictly speaking, it usually does not satisfy ideal axioms. So Rosansky-Witten theory, in a sense, is a little bit bad. So if you want to compute partition functions, for some partition function you can compute, but for some of them you get infinity. So it's not always well defined. But what's interesting in this family is that they can be normalized. Using a discrete action of a discrete group or a discrete symmetry. Indeed, this space has a symmetry group of Z5 acting, and this action, I think, is triholomorphic and certainly preserve the relevant homomorphic symplectic form that you use to define Rosansky-Witten model. And after regularizing this, you will get now a well-defined but non-unitary 3D TQFT. So what is the 3D TQFT you get from this? In this particular example, you get the 3D TQFT associated with a 2D CFT. Called the 2,5 minimal or Virasora minimal model. And one special thing about this minimal model is that it is non-unitary. It has no, it's not logarithmic, but it's rational, but with negative central charge. for the case that k equals to 4, the modular space looks like the following. It's again an elliptic surface, but now the singular fiber will look like the following. And the action is now a Z3 action. And in this case, you will also get a 3D TQFT, and the corresponding 2D theory is given by affine Cosmudi algebra, SL2, but at negative level, minus 4/3. This is an unmissable level, so the CFT is still looks like a rational CFT. And one can define some 3D TQFT that correspond to this 2D conformal field theory. Yes.
But there's no Planck's constant here, right? So these are just numbers.
Yeah.
The invariants are numbers.
Yeah. So the
Not functions. Right?
3D TQFT are supposed to be rigid. So
So you don't get Q series or anything like that.
so these are not going to be Q series. These are not going to be Q series. If you want to compute partition function, it's just a number.
Integers?
No, they're not going to be integers. So, curiously, this theory is related via Galois transformation to G2 Chern-Simons theory at level 1. So that you can have a sense of what the partition function would look like for this theory. In fact, there are many. So these are already the two starting theory in two infinite families. So for k odd, recall again that k is the number that tell you that specify for the spectral curve. For k odd, then there is an action of the k plus 2 on the well-taken model space, and then this correspond, and this will give you 3D TQFTs that are related to 2 comma k plus 2 minimum models. And for k even, there will be action of z k plus 2 over 2 on the model space. And these are related to the 3D TQFTs that correspond to the 2D CFTs that has Bn algebra as a symmetry, which is quantum Hamiltonian reduction of the Wn algebra. But there are actually a lot more theories like this. So even here, you can already ask. So n is determined by k, and most likely it's something like k plus 2 over 2. But since I didn't give you the definition of Bn algebra, probably I don't need to tell you what exactly n. That depends on the definition. Right? It's related to Dynkin diagram. So there's also Dn algebra. So apparently, quantum Hamiltonian reduction of doubling algebra has some kind of ADE classification. So
It's a double algebra for
What series?
D?
no, it's oh. So the question is whether this can be regarded as doubling algebra for type B group. Maybe that's the case. Actually, I don't know about this, but it's the quantum Hamiltonian reduction of WN algebra. So now there are infinite families of TQFTs, and maybe we can ask this question that Renat and Stephos love to ask, whether there are analog of volume conjectures or AJ conjectures for these infinite families. So for all these Carré algebras, we understand the modules pretty well. So it makes sense to take some large level limits while also taking some large color limit, but keep some ratio fixed. So it makes sense to formulate volume conjecture and AJ, perhaps also AJ conjecture. But in fact, these are only two families in a very, very large class of theories. It turns out that for any for pair of Deakin diagrams where gamma 1, gamma 2 are Deakin diagrams of type ADE, you can get 3D TQFT in a similar way. And in a sense, this is a little bit like Chern-Simons theory. In Chern-Simons theory, the data is specified by group and then a level. And here, there are two two AD diagrams that you want to specify. And one is playing, in a sense, a role of the group. One is playing, in a sense, a role of the level. And even better, there is symmetry. If you switch these two, they will define the same 3D TQFT. So there is some analog of level rank duality here also. But these are all going to be non-unitary 3D TQFTs. So they are not like Chern-Simons theories.
Chern-Simons theory is a different root of unity, not equal to pi A.
So
it's not unitary.
in some cases, indeed, they turn out to be Chern-Simons theory at different root of unity. In the example that I had before, if you consider, for example, G2 at level 1, and then at different root of unity, you can recover this 2,5 minimum model. But it's not clear whether all of these are of this type. So it seems that if you just maybe count numbers, they are a lot. So the landscape look pretty different. So this is still a subclass of the class of theory that can be used to construct 3D TQFTs. And it seems that that landscape is way larger than the landscape of Chern-Simons theories. So it seems to me that it's almost certain that there are a lot of new stuff. So to give you some information about another series of in this huge family, consider A1, comma D2n plus 1, then this will turn out to be related to, again, SL2 at level 4n minus 2n plus 1. And the example that we give that has this k correspond to the family of A1, A, K minus 1 theories. So you see that in the case that K is 4, you have A1, A3 theory, and we know that A3 is the same as D3, and indeed here there's also exceptional isomorphism of TQFTs, such that these two turn out to be the same, and indeed this nicely corresponds to statement about chiral algebra, like some Bn algebra just happen to be affine Kazhmoudi algebra at admissible level. So I think my time is up. So, but let me make one final remark. It seems that these two ways of reducing Z hat to WT invariant at different level, and then to different families of non-unitary TQFTs can be, some aspect of this can be understood from representation theory of Daha. I won't be able to give you the full details of this story, but the idea is that there are, for representation of Daha, usually they are infinite dimensional, but sometimes there can be finite dimensional representations. So Daha is labeled by two numbers, Q and T, and if you take Q to be root of unity, then you can get some finite dimensional representations, and these are related to WT invariants. But there are different reductions that you can do. You can consider T equal to plus minus Q to some power, and then this is related to this new family or new families because they are plus minus sign of TQFTs. So let me end here. Thanks.
No questions for this?
There was something for pairs of Lincoln diagrams of varying types. It's the logic of pi systems. Is it? There is something called the logic of pi system related to pair of Lincoln diagram of varying type.
Okay.
It's some periodic transformation, Boston transformation. I have no idea what is physical origin.
Interesting. So the reason to relate this to, so there's a way to go from, so a pair of AD Lincoln diagrams can specify Calabi-Yau3 singularity.
Ah, yeah, okay, yeah.
And then there is a way to go from string theory plus Calabi-Yau3 singularity to a 4D theory and then to a 3D TQFT. So that's how this works in physics. But then there is also some relation between 3D theory and chiral algebra. Maybe the thing that you described is the counterpart of this for.
Related to mirror symmetry for 3D.
So in some cases, the mirror of this can be understood, but I don't know how to use the mirror of this to.
No, I mean mirror symmetry for 3D
equals 4 theory.
No.
Yeah, so this story is related to 3D symplectic duality. In a sense, this is the 4D version of the 3D symplectic duality. So 3D symplectic duality tells you that Coulomb branch and Higgs branch talk to each other in 3 dimensions. But this kind of correspondence tell you actually that Higgs branch that has something to do with chiral algebra like this also talk to Coulomb branch, which is the target of the Rosansky-Witten model. So there is some kind of interesting geometric representation theory going on.
I just wanted to ask if the SL2C hat at this minus level, is that the same as PHMV with that ruler unity? In BH and V makes sense for not just the first primitive invariants, but all of the primitive invariants?
I don't know the answer. My understanding is that understanding the model tensor category that can come out of the category module from this is not a completely solved problem. So Thomas Krusig are writing long papers on this, and he told me that there are several steps until you get to a model tensor category that define the 3D TQFT. But it could happen to be the one that coincides with the one that you have in mind. That's possible.
So, for example, this one, does it have other kinds of asymptotics?
For this one, SL2 at level -4/3. This the model tensor category has 3 simple objects, and I don't know whether that's already equal or give you a mismatch to the thing that you mentioned. So 3. From category algebra, there are 3 admissibles. And then in the corresponding model tensor category, there are 3 simple objects correspond to these 3 admissible representations.
No more questions? Let's thank you again.